Hello everyone. Welcome to this video. In this video, we are going to learn about the Neural Ordinary Differential Equation using OpenMathAI. So, let's get started. What is a Neural ODE? A Neural Ordinary Differential Equation is a supervised deep learning algorithm used for continuous time dynamic system modeling, regression, and time series prediction. It is designed to learn how the state of a dynamic system evolves continuously over time. Unlike traditional neural networks, which learn a direct mapping from inputs to outputs through a fixed number of layers, a Neural ODE learns a continuous rate of change of the system state using a neural network. An ODE solver then integrates these learned state changes over time to compute the future system state, allowing the model to accurately represent dynamic processes. During training, the Neural ODE receives the input variables, feedback states, and automatically generated derived state features. It learns a continuous system dynamics by estimating the state derivatives, while the ODE solver repeatedly integrates these derivatives to minimize the prediction error. During prediction, the model receives new input data, estimates how the system state changes over time, integrates the learned state derivatives, and predicts the future system state without retraining the model. We will use a DC motor dynamics dataset for the Neural ODE model. During training, the Neural ODE learns a continuous relationship between the applied voltage, motor speed, and motor current by modeling how the current motor state evolves over time. The automatically generated feedback and derived state features help the model accurately represent the motor's dynamic behavior. Once the model is trained, OpenMathAI uses these learned continuous time dynamics to predict the motor speed and motor current for new operating conditions without retraining the model. So, let's get started. Open OpenMathAI. Click Create New Project. Enter the project name as Neural ODE. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the inputs, feedback states, and targets. There is also a feature called Ignore, which can be used for columns that should not participate in model training. OpenMathAI can also create derived states from the sequential data. These derived states may include lag values and derivative values. These derived states are used in the feedback section to help the model understand how the DC motor changes from one time step to the next. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature is signal diagnostics. There is a free columns. First one is column it tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the Neural ODE model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, Test Data Split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see three types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of actual and predicted output. Click Math and Code Preview to view the mathematical model generated by OpenMathAI. Open the Math view to visualize a complete Neural ODE architecture. Maximize the window and scroll down to see. The preview displays the Neural ODE architecture, mathematical equations, generated source code, and a detailed explanation of the prediction process. The visualization shows how the model receives a current time, input voltage, motor speed, and motor current. The neural state function estimates the rate of change of motor speed and motor current. The ODE solver then integrates these learned derivatives over time to calculate the next motor state. The feedback states provide information about the current operating condition of the motor, while the derived states help describe how the motor behavior is changing over time. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format. ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.